Okay, welcome all. So you've been through a pretty mathematical week or lecture last week where we discussed the Fourier transform at length as probably the most important unitary transform, and we've been discussing its special properties, what makes it unique amongst all unitary transforms. However, the basis functions used in this transform are global. We looked at those plane waves, and the coefficients associated with these plane waves tell us how much of that frequency is in the image, and it tells us the phase of the wave, but a single coefficient gives us no information whatsoever about the localization of certain features in the image. It's only when we take multiple of these plane waves together that we can learn something about where, for instance, an object lies in an image. Now, this is perhaps not very intuitive, and in some ways, or in some applications, also not the most natural representation. And today we will talk about the wavelet transform as a means of bringing locality back. So the wavelet transform is an attempt to get both spatial and frequency or scale resolution in a transform. This will be the main topic of the day, but before we get to that, I have to add a few more properties. I want to start by discussing the relation between the different kinds of Fourier transforms there exist. Actually, we talked about the discrete Fourier transform only last time, but the one that is mostly used in pen and paper work is actually the continuous Fourier transform. And I want to establish the relation of it with the discrete Fourier transform. So let's consider a signal in space or in time, which is associated with a continuous Fourier transform that lives in reciprocal space or k-space. And in the continuous Fourier transform, we're considering signals that are continuous both in space and in reciprocal space. So I'm making these up, of course, and I've been careful here in the spatial domain to use a signal that is, well, its energy is fairly localized. I'm not saying that it strictly has a finite support, but I localize it so as to make my next drawings easier, as you will see in a moment. Now, I can discretize the signal, and this discretization can be represented by multiplication with an impulse train. So this is just a series of Dirac impulses, and it continues to infinity. So the name of this beast is an impulse train or a comb, or there are many other names that have been given. And the operation here is a mere multiplication. So what I now obtain is a version of my signal that is discrete in space, but not necessarily discrete in amplitude. Something like this. Discrete version of what you've seen before. Now we know from the convolution theorem that if I multiply in space with such a with any filter, this amounts to a convolution in the Fourier domain, and without proof I'm stating that the Fourier transform of such an impulse train is again an impulse train. But this time here we have a convolution. And this convolution, we can consider the width of this comp. In fact, if you look at the distance here between two of these impulses, there is a scaling theorem which says that when you compress one function in space, any function in space, then its Fourier transform will become dilated. So if I expand this width, I will shrink that one, and vice versa. So let's say that I've chosen an impulse train in the spatial domain where the impulses are fairly closely spaced, which means that in the Fourier domain I will convolve with something where the impulses are fairly widely spaced. Here, in fact, I've tried to space them so widely that we won't have too much aliasing. So I now have the same power spectral density, but convolved. So there's its ghost neighbor, its aliasing neighbor, and so on. This goes on to infinity. So we are now discrete here in the spatial domain and periodic. So discrete and aperiodic in the spatial domain, and continuous and periodic in the reciprocal domain. Now this first set of transforms was called the continuous Fourier transform. These are still each other's transform, but that is the discrete-time Fourier transform. And I will later write down the formula for the continuous Fourier transform. So here we use an integral for the forward transform and an integral for the backward transform. Or maybe I write it here next to the symbol. So we use an integral in the one direction, integral in the other direction. Here we have an infinite summation in the one direction and an integral in the backwards direction. Next, we can go from a signal that is periodic in the, sorry, to all those people using paper here. Next, we can go to a signal which is discrete both in the spatial and the reciprocal domain, which is what we need if we want to work with computers. So we use the same trick again. This time down here, I am multiplying with an impulse train. And if I multiply with an impulse train in the reciprocal domain, I have to convolve with an impulse train in the spatial domain. Okay, I'm a little lazy and copying over from here. So here's the original signal. And I now also thanks to this convolution operation, I also need to repeat the signal on either side up to infinity. We have the periodic boundary conditions. So here it is again. And there it is again. Okay, and my signal is now discrete and periodic in the spatial domain. And that also holds for the reciprocal space. It was already periodic before, and now it becomes, in addition, discrete. So I'm now sampling this power spectral density here discretely. And have to repeat on either side. Okay, and these are again each other's transform. I now have a finite summation here. Let me say explicitly this is a finite sum and a finite sum, whereas here before this was an infinite summation. And that is the transform we discussed last time. The discrete Fourier transform, or DFT for short. Sorry, terrible writing. Now this is intimately related with the sampling theorem, because let's look again at the first stage here, where we sample the continuous signal discretely. Obviously, if my signal has very fine details, let's say, you know, there's a tiny blip sitting here somewhere on the signal, I might miss these tiny blips if my sampling interval is too coarse. So that would amount to a loss of information. Can you explain in the Fourier domain how this loss of information will manifest itself? Yes, and that's correct. Less amplitudes for high frequencies. And can you argue in this picture here what this will mean? So let's consider here a function which has a few blips. You know, it's similar to the one that I've drawn before, but with a few sharp edges on top. Can you explain what its spectral density will look like relative to the one that I've drawn here before? Y in the middle, so this is zero frequency. So this is the wave number K. So, but you said more mass in the middle, right? But the middle here, those are the low frequencies. So if I have a similar version here, but with extra blips, it means that I have more energy in the high frequencies. My power spectral density will decay more slowly as I go to higher frequencies. Okay, and what does it imply here for this picture? Oh, what I've sketched here has been the magnitude, because I cannot draw complex numbers very well. Oh, you're saying that my original signal here should not have any DC term? So if my original signal here integrated perfectly to 0, then yes, I would have 0 DC term. But you know, I made the left lobe a little bit larger than the right lobe, and so on. Or you know, I made the positive parts larger than the negative parts because I wanted the DC term here. So what I wanted to get to is the following. If I now convolve the signal that you see here, which has a power spectral density that tapers away slowly as we go to higher frequencies, then we start to see overlap here between the power spectral density in the unit cell and its neighbors. So the sum, or you know, the result of the convolution would look something like that. But it would actually be an addition between, you know, a term that belongs to this side and a term that belongs to the other side. But after this convolution, we can only observe the sum of these two terms. So let me magnify this picture here. So let's say the result of the convolution is to replicate my power spectral densities, but I'm also adding them up. So what I see as a result of the convolution is an overall signal. Let me draw that in green, which looks something like that. And now, so this is the frequency 0 minus 2 pi, and it goes on the same way in the other direction. So now what I can observe is only the green signal, where at some specific frequency here, I observe the sum of this power spectral density and that power spectral density of the neighboring cell. And hence, I have some loss of information. And what the sampling theorem says is that a discretization or a sampling of a signal is lossless if and only if the resulting or the associated convolution of the power spectral densities leads to no overlap at all. And that is typically true for true low-pass signals, so signals which have no energy whatsoever in high frequencies. But it's actually also true for certain bandpass or high-pass signals. All right. So we have the continuous Fourier transform, the discrete-time Fourier transform, and the discrete Fourier transform. And the picture is not quite symmetric yet, because I could also do the following. I could also, rather than multiplying with the continuous signal with an impulse train, I could also convolve it with an impulse train. We'll see that in a moment. Or I could multiply its Fourier transform with an impulse train. Okay. Great. And this will give me a signal which I'm too lazy to draw now, which will be continuous and periodic in the spatial domain, and which will be discrete and aperiodic in the reciprocal domain. And from there, I can go here by convolving with an impulse train and multiplying with an impulse train, respectively. Okay, and these are also each other's Fourier transform, and they have a name too. This is the Fourier series. Where I have an integral over a finite interval in the one direction and an infinite summation in the other direction. So, big picture of how these relate to each other. Do you have questions? So we proved the convolution theorem for the case of the discrete Fourier transform, and an analogous theorem holds for the continuous Fourier transform, and actually for any of these transforms. It's fine, don't worry. So all of these theorems say that when you convolve in one domain, this corresponds to multiplication with its Fourier transform in the other domain. Now the Fourier transform always is invertible. So the Fourier transform, yeah, so the Fourier transform, we have one here and one here and one here and one there. These always are invertible. However, to go from here to here, that may not be invertible if you subsample. Okay. More comments? No, no, because we have the scaling theorem. So, which says that if I have I'm now using continuous notation. If I have a function f of t, which is the Fourier transform of some function of k, then if I take this, its Fourier transform is given by, and then modulo the constant is also, so the normalization constant is also affected by this parameter alpha. So if I make my, so let's say for alpha larger than 1, this would be a compression in the spatial domain and a dilation in the Fourier domain, and vice versa. So for alpha less than 1, this would be a dilation, and this would be a compression. And now I will try and say that again in pictures. Let's say, well, I think you can imagine it. So if I sample my original function at higher frequency, it means that this impulse train here, sorry, it means that this impulse train here becomes more widely spaced. Yeah. So because these impulse trains are each other's Fourier transform by the convolution theorem. So multiplication with a filter corresponds to convolution with the Fourier transform of this filter. And if I make this impulse train narrower, then I make that one wider, which leads to a broader spacing, so and gives less overlap of the spectral densities and so on. Thanks for clarifying. Any further questions? Okay, then I want to look at some of the most important Fourier pairs. So let's say if I have a function f of x in the spatial domain, and I'm now giving the continuous Fourier transform. So f of x in the spatial domain corresponds to a Fourier transform f of, I'm using here xi, this is the continuous Fourier transform, and I want to give a few important pairs. So the rectangle or the box function is centered around 0 in the spatial domain, and I should use a function a here to indicate its width, and then its Fourier transform is that the sinc of xi over a, where the sinc is defined as follows. This is the function that you've surely seen before. So it is, sorry, something disappeared here. The function is 1 at the origin, and then has 0 crossings at all other integers. Oh, this is ugly. So it looks something like this, and so on. And overall it has a, as you see, it decays as 1 over, so if this is xi, overall it decays as 1 over xi. And this is important for interpolation because it works both ways. So if I want to low pass filter by multiplying with a box in the reciprocal domain, this corresponds to convolving with the sinc in the spatial domain. This was the continuous case. The discrete version has a name of its own. This is the Dirichlet kernel, which is discrete and periodic. Oh, kernel, it's just, you know, it's a generic mathematical term. So sometimes used for the kernel of an integral, or sometimes it's used for filters. So no, kernel has multiple uses. Okay, so there's an important one. Then I want to mention the Gaussian. So if I have e to the minus alpha x squared, this is some normalization constant times a Gaussian again. And I also want to mention the impulse. So if I have a single impulse sitting at the origin, its Fourier transform is constant 1. And by the shift theorem, you know that if it's not sitting at the origin but somewhere else, this corresponds to a complex plane wave in the reciprocal domain. And finally, the impulse train. So this is a capital T, which should give the, or it doesn't matter. T here is the period of this impulse train. Here you again see the scaling relation. So here T is in the numerator and there it's in the denominator. If I make one wider, the other one will become narrower. And typographically, this is sometimes represented by a Persian letter. So a letter from the Persian alphabet, which is called Shah. And I think this notation was first used by Bracewell, who wrote an early influential book on, well, early means late 20th century, which is not that early, but who wrote an influential book on the Fourier transform and its properties. Okay, so if you deal with such distributions, there are some mathematical finesses, but I'm ignoring them for now and simply want you to remember that an impulse train is an impulse train and a box function corresponds to a sink. And if you know that, you can actually infer many other interesting Fourier pairs. So as an example, let's say if you are interested in the Fourier transform of this triangle, any ideas on how to do it? Do you have one? So do you know how the triangle can be related to the box function? Exactly. So it's a box function of half its width convolved with itself. And so the Fourier transform of this will be a sink pointwise multiplied with another sink, which gives you a sink squared, which if you draw it, looks something like this. So still decaying as 1 over xi squared this time. Faster decay and all positive this time because I've been squaring. Okay. So as the last thing before the break, I want to talk about derivatives. There is a theorem for those also, and let me argue again in terms of the continuous Fourier transform. I'm writing g of x in terms of its inverse Fourier transform. So this is the inverse continuous Fourier transform. Then now taking the derivative here, which by linearity of the derivative operation, I can pull here into the kernel of the integral. And then taking this derivatives gives me thinking about the sign here. Thank you. Thanks very much. And that gives me the sign that I was expecting to see. You've made my life a lot easier. So this is now the yes, thank you. So this is the inverse Fourier transform of not the original signal, but of the original signal multiplied with I to pi. Okay, that's important. Okay, so more generally speaking, if I take the nth derivative, then I have to take this to the nth power. So the, or let's say the mth derivative has this Fourier transform. And it is this multiplication. So let's say this is k and this is here. I'm drawing the imaginary axis. So this is what my derivative operator does, and if I multiply with this if I multiply Fourier transform with this, because it goes through 0 here, it means that I suppress the DC term of any signal, which is what we expect because constant offsets disappear under the derivative. Moreover, we see here that it amplifies the high frequency content in your signal. So it, generally speaking, makes your signal look rougher and rougher as you take higher and higher derivatives. And this means that if you deal with the real signal, taking higher derivatives typically gives you problems with noise. The reason I'm saying that is, let's say in some typical signal you have perhaps a spectral density which looks like this. So this is the power spectral density of my signal, of the true signal. But in addition to that, I might have noise, for example, white noise that might come from the sensor or from other sources. Now what I observe is the sum of the two. So the observed signal looks something like that. And if I now multiply it here with this function, then I will amplify the noise more than the signal in these high frequency regions. Well, I will amplify them by the same factor, but since I have much more noise, my overall result will look a lot noisier. And this is why, in general, from real signals, it's hard to estimate higher derivatives, or it's hard to estimate higher moments. Because these moments and derivatives, they're also related to each other. Because in statistics, you can take something like the Fourier transform of distributions, and the derivatives of these distributions are related to the moments that you see in the original domain. So this is why in the real world, if you take a derivative filter, you usually don't use the one that I've shown here. But let's say our signal is discretely sampled, or at least we have a periodic Fourier transform, but you typically use something that either goes to 0 or to some less extreme value than the one that I've shown here. Okay, so there are different approximation orders. Well, by periodicity, eventually I need to go. Sorry, this is becoming a mess. By periodicity, I eventually need to go to 0 at frequency k. But you can do so using different approximation orders. And these filters or different approximation orders that I've shown here, if I look at the discrete filters in the spatial domain, they will have different length. So this one here, I can represent by a tab 3 filter, a filter with just 3 coefficients, but the others will require filters that are less well localized in space. And that also means that if you have a real edge somewhere in your signal, you might see these ringing artifacts far away from the edge, which is not desirable. Another reason to use an approximation of this ideal derivative filter. The ideal derivative filter in the spatial domain decays very, very slowly, only as 1 over x. All right, so this is how to compute the derivative. And I have here a couple of applications. First one is a picture from this textbook by Bernd Jenne. You see a still image out of a video sequence, and this video sequence means that really we have a space-time volume. So we have the axis called x and y, and then I have time in the 3rd dimension. And I'm now looking at this slice here out of this space-time cube. So the slice here is the one shown down there. And if you stare at it for a bit, you can interpret what's going on. So we have to agree which direction is time. Let me argue that time here is going in this direction. We also have a red light somewhere, so it looks like there were a couple of cars that were stopping at the red light, and then the first one started, and then the second one started, and then a little bit later, the third one started, and this apparently went around a curve which is still visible in the image, and then there was one coming which had to stop before it could go on, and there was one which had to decelerate, but then eventually could continue without stopping all the way. And then we have the continuous background, which is not moving at all, so constant background. So here we have something that's apparently in front of the cars. And then we have these funny wiggles here. I think these are the leaves that are, blowing in the wind. So this is, another look at video. And if you now want to estimate motion, so velocity, in this kind of representation, the velocity of an object naturally translates to its, to an orientation in this space-time volume. And to estimate orientations, you want to use derivatives. Actually, you want to use something like the structure tensor that we will talk about later in the semester. But even for that, you need derivatives. I have another example here. Here is a camera array, and that is useful to acquire light fields. You can either literally use a full array of cameras, which is pretty expensive, or you can alternatively use a sensor with a microarray of lenses sitting on the sensor. And in either case, these devices allow you to measure not just how many photons arrive at a pixel, but also from what direction these photons came. And here I have images from Bastian Goldlücke and collaborators who are working here at the Institute. So on top is some, technical device. And then in the bottom, you see a 2D cut through the 4D light field. So this cut corresponds to the line that's shown here. And note that we have some depth differences in this image. And these depth differences, they translate to different angles. So you see that if you look closely here, we have different angles. Or here there's another example of a pretty light field. And down there, the depth that corresponds to each of these pixels. So here the depth has been color-coded. And in such a light field, to estimate depth from the raw data, you need to find the orientations. And to get these orientations, you want to use, or you want to compute derivatives. And this is what the derivative theorem tells you how to do, also in multiple dimensions. So this multiplication trick that I showed here works in one or in more dimensions. All right, any questions? Yeah, so what you just described is how to do taking the derivative in the Fourier domain, exactly. Yeah, so if it's going to be, if you just want to take the derivative, then it depends on your filter size, if it's faster to do it in the reciprocal domain or in the spatial domain. If you want to use a high approximation order, this would mean a very large filter in the spatial domain. And then convolving to, an image with a large filter in the spatial domain is slow. You would definitely be well advised to do that in the Fourier domain. If you have a very compact filter, like -1, 0, +1, it may actually be faster to do it in the spatial domain. You would have to test on your architecture. But it is, good to know this principle anyways, because oftentimes taking the derivative is not the only thing you want to do, but you have other operations also. And these other operations may be faster in the Fourier domain, and then you can do take the derivative in the Fourier domain also. Yeah, if you want really the true derivative function here, it corresponds to, or it has a filter that has a support as large as your original signal in the spatial domain. And doing that in the spatial domain would be very slow. So it would be yeah, an n² operation where n is your number of pixels. And here you can do it in n log n. Okay. So you have earned your break, after which we will finally leave these stationary representations. So in Fourier transform, you always have implicit this assumption that the signal really is stationary. And we will then look at time frequency or time scale transforms, in particular at wavelets.